Continuing with the normal distribution, in particular the standard normal distribution, we're going to look at applying the tables from the textbook that we need to find certain probabilities. So make sure you have your textbook out, or you can access some sort of normal distribution table. So here, first thing that we want to do is find the probability that z is less than 1.64. And so I want to draw a picture that represents that. Over here, you recall the distribution of z, the standard normal, has a mean of 0. Somewhere over here is 1.64. If I go out to 3, I'm going to get pretty close to where the PDF starts to touch or gets real close to the horizontal axis. So this probability is the area under the curve to the left of 1.64. So that area is, that I've got shaded, the probability that z is less than 1.64. Okay? Now how do we find that? Well, there's not a formula that gives us that quantity. We're going to use the table from the book. And so I've got a PDF of the book here. I'm going to try to open up. There we go. So there's the PDF of the book. Front part of the book there. You notice that it's split up into two tables. Table 1 and Table 1 continued. But the first page of Table 1 gives areas under the curve to the left for negative z values or negative z scores, and then when we get to the second part of the table, it gives areas under the curve to the left for positive z scores. Okay, this is kind of your legend up here. It gives you a sense of what that's all about in terms of what it gives a shaded area to the left of a given z score. Okay, so I want to go to 1.64 here. I want to go to z equal 1.64. So looking at the left column here, the leftmost column that gives me my z values, I'm going to scroll down. Let's see here. Well, okay. I was trying to draw on that. Okay, so coming back here. So I won't draw on it, but if we go down to z equal to 1.64, here is z is 1.6 there, and then I scroll over to in the top row of this table, 0.4. That's the 100th digit. The 10th digit is the 6th there, and so, or the 10th place there. So I've got 1.60 would have a left area of 9.452, but 1.64 has a left area of 0.9495. And so if I go back to my PDF here, that's 0.9495, and this is from the table. Okay. The probability that z is less than 0, that's the area under the bell curve to the left of 0. That's what that probability is. Well, we don't even need the table to figure this out. We know the total area under the curve is 1, and that the graph is symmetric about 0, so the area under the curve to the left of 0 is 1/2. If you want to look at the table, you can, and you look here at z equals 0, the corresponding left area is 0.5. All right. What about the probability that z is bigger than 0.76? So this is the area under the curve. To the right of 0.76. So the greater than tells me I'm dealing with a right area. So that probability is that area there. Well, if I look up a z-score 0.76, the table is going to give me this area here. So let's using our table here. Go to 0.76, and I'm going to be there. It has a left area of 0.7764. Okay. So coming back to the PDF here, the area under the curve to the left of 0.76 is 7764. Was that what that was? I forgot. Yeah, 7764. Okay, so then this area to the right of positive 0.76 is 1 minus 0.7764. And so you take the difference there, and you get 0.2236. Okay, so we had to, you can think of this as we use the complement rule at this stage right here. 1 minus the probability that z is less than 0.76, or if you just want to think of it in terms of areas, you can as well. The table gives us left areas. We got this from the table, so we subtract that from 1 to get the right area. Okay. All right. Probability that z is between. Let's make that a pin. The probability that z is between negative 1.44 and 2.27. That's the area under the curve that I want, area under the bell curve. Now, again, the table does not give me this kind of area directly. It just gives me left areas. But I can couch this problem in terms of the difference of two left areas. If I take the area under the curve to the left of 2.27 and subtract off the area under the curve to the left of, let's see if I can get a different color here, to the left of negative 1.44. Doesn't look like a can. So this area here, what's left over is the desired area in the middle. Okay, so I'm going to take the area under the curve to the left of 2.27, look that up in the table. Z equal to 2.27. Which column does that put me in? That puts me in, barely fit, right here in that column there. So that's 0.9884. Okay. So here we have 0.9884 minus, going back to our table, I forgot the z-score. The left area associated with negative 1.44. So I'm going to come up here, go to the first part of table 1, negative 1.44, negative 1.4, come over to the fifth column here, 0.0749. Okay, so that's 0.0749. Take the difference there, and I get 0.9135. Okay, so that's the area under the curve between two z-scores. Had to use the table in a unique or in a clever way to get that particular area. Okay, we can also use, let me minimize that, we can also use the table in the front of the book to find a particular z-score that corresponds to a right area or a right probability. And so when we think back, this page here dealt with finding an area given a z-score. Now we want to find a z-score given an area. And so some notation to this is we are interested in this z sub alpha, and z sub alpha on your standard normal curve is the value of z. So it's a particular value of z. Okay, it's the value of z such that the area under the curve to the right of that value is alpha. Okay, and so the area under the curve to the left of that value would be 1 minus alpha. So let's look at a couple of examples. Let's find z sub 0.10. All right, so z sub 0.10. The subscript here is pretty small, and that's a right area. So I know I'm going to be out in the right tail of this distribution. Okay, so this is a particular z value. The area under the curve to the right is 0.10. All right. So if I want to use the table at the back of the front of the book rather, I need to use it in an inverse way. Okay, I want to find a z-score that gives me a right area of 0.10, or equivalently a left area of 0.90. So if I go to the table here, I don't look for I don't choose a z-score first. I look in the table and look for a left area that's as close to 0.90 as possible. So looking in here for 0.90, 0.89, 0.898, 8997, and so I got 8997 and 9015. I'm going to go with the 8997. That's closer to 0.90. The z-score that corresponds to that is 1.28. Okay, so let's see, 1.28 there. So this value is actually 1.28. The way we think of 1.28 is it's the 90th percentile on this standard normal distribution. Another one here, let's find z sub 0.05. Again, we have a bell curve. Mean is 0. Z sub 0.05 is going to be a little further out in the tail than z sub 0.10. But the area under the curve to the right of this value is 0.05. The area under the curve to the left of this value is 1 minus 0.05. All right. So I'm going to come back to my table. I'm going to look for a z-score that has a left area close to 0.95. Or closest to 0.95. So let's see, 0.9484, 0.9495, 9505. So it's these two values are equidistant from 0.95. So I could choose either one. What I'm going to do is actually interpolate between 1.64 and 1.65. Okay, so and when I do that interpolation, it would be 1.645. Okay, another little problem here. Find the z-scores that separate the middle 68% of the distribution from the area and the tails of the standard normal. So I've got the standard normal curve here, and this is a little bit different in that I've got two z-scores that chunk out in the middle of the bell curve 68%. So in between these two z-scores, the area under the curve is 0.68. Now, these z-scores here are going to come out from 0 in an equidistant manner. So here I've got a z-value, a particular z-score, and over here I have another one. Now, let's see, how can we figure out what would the subscript be on that z-score? Well, the area between this z-score, I'm going to have z sub question mark, I don't know. This one over here in the corresponding left tail is going to be negative z sub question mark because of symmetry about 0. But I know the area under the curve between these 2 points is 0.68, so that the area out in the tails has got to be 1 minus 0.68. The area out in the tails then is 0.32, and that tail area is equally divided in the left and the right tail. So this tail area is 0.16, this tail area is 0.16. Okay, so I am interested in, I can now talk about, hey, this is z sub 0.16, and this is z sub 0.16 also, or negative z sub 0.16 in the left tail there. Z sub 0.16 here in the right tail, I'm going to look for a z-value that has a left area of 0.84. So if I go to my table here, look for a left area of 0.84. How close can I get? So 0.8413, 0.8389. This is a little bit closer to 0.84. The corresponding z-score is 0.99. So I'm going to go with that. That value is 0.99. Hence, negative z sub 0.16 is negative 0.99. Okay, so the two z-scores are negative 0.99 and positive 0.99. And if you look at this and you think about, what is this saying? It's saying that roughly between negative 1 and 1, 68% of the area is contained for the standard normal curve. And this should look somewhat familiar because that's what we had in the empirical rule. That 68% of a data set is between plus or minus 1 standard deviation of its mean, and 95% is within plus or minus 2 standard deviations of the mean, and so forth. And the empirical rule finds its basis in the normal distribution. Okay, we see this fleshed out here for 1 standard deviation from the mean. Okay, so we've dealt with the standard normal curve. Let's look at the setting where we might not be dealing with a standard normal distribution. Suppose we have a normal distribution where the mean is 5 and the standard deviation is 1. Okay, so the mean isn't 0, so we're not in the standard normal setting. How do we find the probability that x is less than 6, or the probability that x is between 2 and 6.25? How do we find those sorts of areas? Well, the table we have for the front of the book is for a particular normal distribution. Do we create a table for every kind of normal distribution to find these sorts of probabilities? That would That would be unrealistic. And so what's done is we standardize the variable, and so what we're really doing is a mathematical transformation. We will transform any normal distribution into the standard normal distribution. So how do we do this transformation? Well, the way we do this transformation is we run every x value through that formula. We take the x value, we subtract off its mean, and divide by the standard deviation. If we do that, then that transformed variable has a standard normal distribution. Okay, so here's a picture of what's going on. So here's just a run-of-the-mill bell curve centered at mu. This is the distribution of x. Okay, here x is distributed normal with a mean mu, standard deviation sigma. I can go out 1 standard deviation to the right, 2 standard deviations to the right, or 3. I can do the same thing going to the left. Most of the area is between plus or minus 3 standard deviations of the mean. Now, if I take every x value on this axis and I run it through, actually let me put this over here, and I run it through this transformation, x minus, not x bar, x minus mu over sigma, what does that do? Well, I still have a normal distribution. I still have this bell curve. But what it does is, let's start with mu first. If I plug in mu for x, what happens? So if x is equal to mu, then z equals, I've got mu minus mu over sigma. Well, that's 0 in the numerator, so I have 0 overall. So mu is transformed to 0, or mapped to 0. Mu plus sigma, if you plug in mu plus sigma, then what is the z value for that? So I plug in mu plus sigma for x here, and I got mu plus sigma minus mu over sigma. Well, the mu's cancel out, then I've got sigma over sigma, and that is just 1. So mu plus sigma is mapped to 1. Mu plus 2 sigma is mapped to 2. Mu plus 3 sigma is mapped to 3. Mu minus sigma is mapped to -1. Mu minus 2 sigma is mapped to -2. Mu minus 3 sigma is mapped to -3. Okay? So that's how this transformation here is allowing us to go from any normal distribution to a standard normal distribution. A little bit about z-scores that I do want to point out to you. In some sense, it allows us to compare apples to oranges. So take a moment, read the problem set up here. Who runs a faster mile? So we got Billy, the father, and Sam. Okay. Now Billy, 65 years old, in his age group the average mile run is 12, and the standard deviation of that age group is 3 minutes. So the average there is 12, standard deviation is 3. Now Billy's particular mile run time was, or is, 7.5 minutes. Alright. Sam, for him, the average run time, mile run time for him is 6 minutes. No, I'm sorry. That's his run time. The average run time for his group, his age group, is 7 minutes. and the standard deviation runtime is 2 minutes. Now this is for his age group. And his particular runtime was 6 minutes. Now, so clearly Sam runs the faster mile. But the question, so Billy comes along, Dad comes along and says, yeah, son, you're faster than me, but relative to my age group, I might be faster than you. Let's see. So how can we see here? What we can do is we can compute z-scores for both Billy and Sam. The z-score for Billy is 7.5 minus 12 over 3. Okay, so you compute that, you should get negative 1.5. What does that mean? Well, that means that Billy is 1.5 standard deviations faster than the average for his group. Okay, so that's considerably faster than with respect to his group. Now Sam, on the other hand, his z-score is 6 minus 7 over 2. So that's negative 1/2, negative 0.5. What does that mean? That's a negative there. That means that his average time is half a standard deviation faster. I'm sorry, let me back up. His time is half a standard deviation faster than the average run time. Okay, so Sam is faster than his average. He's fast, the average for his group. He is faster than Billy, but Billy comes along. The daddy always comes along. He finds a way to outdo the son. He says, but relative to my age group, I am faster. Okay, so in some sense we are comparing apples to oranges here with z-scores. All right, one more application for the normal distribution, then we'll wrap up the normal distribution here. It has to do with IQ scores. It's very common to model IQ scores with the normal distribution. So I'm going to let X be the IQ score here. And the distribution of X is normal, or we are assuming it's normal, with a mean of 100 and a standard deviation of 16. Okay? Okay, so a few questions here for IQ scores. What is the chance that a person has an IQ score less than 120? So we're after the probability that X is less than 120. If we want to draw a picture of that, we can. Here's the distribution of X, bell-shaped. It's centered at 100, that's the mean. And over here somewhere is 120 to the right of 100. And the area under the curve to the left of that, that's the desired probability. Probability that X is less than 120. Okay. Well, we can't find this area directly because we don't have a table for a normal distribution where the mean is 100 and the standard deviation is 16. We only have a table for the standard normal. So what we have to do is we need to transform our X to a Z. So we need to transform our X to a Z. If we do that here, what happens? Let's see. So I'm gonna do the transformation actually over here with the probability statement. Remember, the transformation is X minus mu over sigma. That's the transformation in symbols that's on the left hand side. What I do to the left hand side, I'm going to do to the right hand side. In numbers, the actual values, 120 minus 100 over 16. Notice the inequality stays less than. That transformation does not affect that inequality. So that equals the probability that now Z is less than 20 over 16, which is 1.25. And so this problem boils down to back to this this other bell curve, this standard bell curve, boils down to finding the area under the curve to the left of negative 1.25 for the standard normal. Okay, so I go to my table here and I look up Z 1.25, so there's 1.25, 1.25 has a left area of 0.8944. Okay. All right. What about the probability that an IQ score is between two values? So Lewis Terman, who developed the idea behind the IQ test, had the designation of quote-unquote normal intelligence if X is between 90 and 109. Okay, so what's the area under that normal curve between 90 and 109? If I want to draw a picture here, I can. Again, the mean, I've got the distribution of X has a mean of 0. I'm sorry, it has a mean of 100. And I'm looking at here the area under the curve between 90 and 109. Okay. Well, like the previous problem, I'm going to transform X into Z so I can use my standard normal table. So I'm going to run everything in here through the Z transformation. So I'm going to have here 90 minus 100 over 16 divided by, or less than, rather, X minus mu over sigma less than 109 minus 100 divided by 16. Okay. The arithmetic for the first standardized value is negative 0.63, and the arithmetic for the second standardized value is 0.5625. So I am looking for the area under the standard normal curve now between negative 0.63 and 0.5625. Okay. So, let's see. Let's get here's negative 0.63 on the standard normal bell curve, positive 0.5. I just need to go up to 5.6. I don't need to go up because that's as far as the table reads for Z-scores. I want that area under the curve there. Okay. So I'm going to look at two left areas. Area under the curve to the left of 0.56 minus the area under the curve to the left of negative 0.63. What's left over is going to give me the desired area there. So I need to look up two values. Okay, so when Z is 0.56, I get a when Z is 0.56, I get a left area of 7123. And when Z is negative 0.63, so negative 0.60, 1, 2, 3, the left area is 2643. Taking the difference there, 7123 minus 2643 is, let's see, let's see if I do the arithmetic here, 0. 0.84, so 0.4480. All right, so roughly 45% of the population, according to Lewis Terman, meets his criteria. Okay, so in 1 and 2, we applied the normal distribution to find an area under the curve. Number 3 is slightly different. We're gonna, so you may want to hit the pause button, read this, attempt it on your own, then come look at it or come watch the video. But Mensa is a high IQ society that admits members if they have an IQ in the top 2%. Okay, so the question here is, what is the lowest IQ a person can have and still be in that society? I'm going to draw a picture that's going to help me out with this. Here I'm interested in, it's a value in the right tail of the distribution. So it's an IQ score that's obviously high in the right tail of the distribution. The associated right area is going to be 0.02. Okay, notice this value x sub 0.02 is going to be greater than 98% of all the other values, but less than 2% of the upper values. Okay, so I want x sub 0.02, or the 98th percentile, for this distribution. Well, how do I get that? Well, I do know that z sub 0.02 is related to x sub 0.02 through the transformation formula. And so if that's the case, I can solve for x sub 0.02. And if I do a little algebra here, I would get mu plus z sub 0.02 times sigma. Okay, this is sigma here. Now, what is mu? Well, I know mu is 100 plus, what is z sub 0.02? I don't have that yet. I can look it up. I know sigma is 16. So I just need to look up z sub 0.02 to get the final answer here. If I want to draw a picture, bell curve, z sub 0.02 is the z value such that the area under the curve to the right of it is 0.02. 0.02, that's it. And the area under the curve to the left is 0.98. So I'll look here in our table for a left area of 0.98. So I'm looking in the meat of the chart. So 0.98 was the closest I can get. Here is 0.9798. That is 2.05. Okay. So that z-score here, this z-score is 2.05. So I'm going to plug in 2.05 there. And so if I do the arithmetic, I get 132.8, or in terms of IQ scores, they're on an integer scale. 133 is that value according to our model. You got to have a 133 or higher to get into this society. Okay, so this is an application of the normal distribution to IQ scores, and wraps up our discussion on the normal distribution. A lengthy discussion, I know. We're going to look at in a little bit, evaluating whether or not a real population is in fact can be modeled by the normal distribution by looking at a sample from that population. Okay, so that's going to be the next lesson.